Well, in this we are going to see the algebra of sets, bit vector representation of sets. First we will cover the algebra of sets. Algebra of the sets is very important to remember. For the subject point of view, you are supposed to remember, there is no other goal. Algebra of the sets. The algebra of set is a fundamental property of set operation and set relations. It is the algebra of set theoretic operations of union, intersection and complementation and the relations of equality and inclusion. So how the combinations of the equality, union, intersection and the inclusion etc. are applicable on various sets in a formulation or in a formula manner, it will be explained in this particular algebra of the sets. The first proposition 1, for any two sets for any sets A, B, C and C, the following identities hold. The first one is commutative law, A union B is equal to B union A intersection B is equal to B intersection A. While coming to the associative law, A union B union C is equal to A union whole B union C. While coming to the whole of A intersection B intersection C is equal to A intersection of B intersection C. These two will fall under the associative law. In case of Cartesian product, associative law will not hold. Okay, we have seen previously. So it differs from the type of operation that you perform. Okay, if you perform Cartesian product, this will not hold. If you perform union or intersection, it will hold. Next one is distributive law. A union of B intersection C is equal to A union B whole intersection A union C. A intersection of B union C is equal to A intersection B union A intersection C, which is called distributive law. Proposition 2, for any set A of universal set U, the following identities hold. A union null, that is empty set, is equal to A, which is called identity law. A intersection union, that is universal set U is equal to A, which is also called as identity law. Complement law, A union A dash is equal to union, that is universal set U. A intersection A dash is equal to null, because you will not find anything in common between the same set and its complement. Proposition 3, for any subsets A and B of a universal set U, the following identities hold. A union A is equal to A, that is idempotent law. A intersection A is equal to A. Next one is dominant law, is A union universal set is equal to universal set. A intersection empty set is equal to empty. Absorption law, A union of A intersection B is equal to A. A intersection of A union B is equal to A. Proposition 4, let A and B be sets of a universe U, then De Morgan's law. Here A union B whole complement is equal to A complement intersection B complement. A intersection B whole complement is equal to A complement union B complement. Double complementation or involution law, that is A complement whole complement is equal to A. Okay, complement of complement is equal to the same. Next one is complement law for the universal set and empty set. Complement of the empty set is universal set. Complement of the universal set is empty set. Next one is uniqueness of complements. If A union B is equal to universal set and A intersection B is equal to null, then B is equal to A's complement. Proposition 5. If A, B and C are sets, then the following holds. Reflexivity. A is the subset of A, which is called reflexive in nature. Antisymmetric. A is a subset of B and B is subset of A if and only if A is equal to B. That means both the sets are having the common elements, then only you can say this particular thing, which is called antisymmetric. Next is transitivity. If A is subset of B and B is subset of C, then A is also a subset of C. Proposition 6. If A, B, C are subsets of set S, then the following holds. Existence of a least element and a greatest element. Null is the subset of A and A is subset of S. In such a cases, existence of a least element and a greatest element. Existence of joins. A is subset of A union B. If A subset of C and B is subset of C, then A union B is subset of C. Next is existence of meets. A intersection B is subset of A. If C is a subset of A and C is subset of B, then C is subset of A intersection B. In your school days or plus 1 or plus 2, you might have seen the solving of these particular rules. However, we are not going to discuss the solving of these rules. We are only highlighting the proper rule or proper proposition for every constraint, and you are supposed to remember these particular rules. The algebra of relative components, proposition 9, for any universe U and sets A, B and C of universal set U, the following identities hold. Well, these are the things you are supposed to remember, and this will be used for the maximization and minimization of the expressions. Okay. So C minus of within the brackets A intersection B is equal to, this is a expansion law. You can say, you can distribute this like C minus A union C minus B, where in case of C minus of A union B is equal to C minus A intersection C minus B. C minus of B minus A, so B minus A can be changed to, or this particular expression, whenever you expand this. So C minus C minus of within the brackets B minus A will become the A intersection C union C minus B. Next one is B minus A within the brackets intersection C is equal to B intersection C minus A, which is B intersection of C minus A. Why? You are supposed to, whatever the expressions we have seen so far, that need to be substituted in the appropriate place, and you are supposed to perform the minimization or maximization. B minus A union C is equal to B union C minus of A minus C. Next one is A minus A is null, because the same set, if you subtract or minus, then it will become null. Null minus A is equal to null, because nothing will be common in both the null and A set. A minus null is equal to A. B minus A is equal to A dash, that is A's complement intersection B. B minus A whole dash is equal to A union B complement. Universal set minus A is equal to A complement, and A minus U is equal to null. Prove that A minus of A minus B is equal to A intersection B. Now how can you prove this A minus of A minus B is equal to A intersection B? So you may start with either the left hand side or right hand side, that is up to you. If you feel that you can solve with the right hand side, okay, you may take up the right hand side and you can prove or you can achieve the left hand side. So this all we are perfectly aware of in the mathematics. LHS is equal to RHS, hence proved. So this we used to write. So you can take any side. So A minus B is represented as A intersection B complement, and for that A intersection B complement whole complement we have made, then it will become, whenever the whole complement was made, the intersection will become the union, and the set which is already having the complement will be nullified, and the one who don't have the complement will become the complement. Then the distribution law was applied, A intersection A complement, union A intersection B, then null union anything will become the same set. So this is the way we can prove this particular expression. One more expression has been given here. Use set builder notation and logical equivalence to establish the first De Morgan's law. So this is the most common question in the school days and plus 1 and plus 2, proving of the De Morgan's law. So the further explanation I think is not required for you. So just you go through this slide. So finally you will get the A intersection B of whole dash is equal to A dash union B dash. Let's prove the following statement. Universal set intersection A within the brackets, okay, union within the brackets B intersection A is equal to A. Now union intersection A, so how you are supposed to prove this? So use the commutative law. Okay, if you use the distributive law, what will happen? If you use identity law, how it can be reduced further? Then finally it will come to the identity law. So these three laws will be covered in the proposition 1 and 2 itself. In the same way, one more thing, that A intersection union intersection null union A complement, okay, will become the null. So here also identity law has been used, distributive law used, again identity law used, complement law used, idempotent law used. So here, so this is the way of reducing the statements. And one more example here, A minus B whole complement is equal to A complement union B. Okay. So they have changed it to the difference. So A minus B whole complement was replaced as A intersection B complement whole complement is equal to A complement union B. Now further they expand it as A complement union of B complement complement. Then what will become? B complement complement will become the same set. So A complement union B. So where we will get the involution law. So can you prove this A minus B is equal to A minus of A intersection B? Can you do this? Notation of sets. How to represent or how to use these particular sets in computer science? We already deal with the computer science. In computers, the information will be stored in terms of binaries. Binary means to the base 2. Okay. So you might have seen in the first year subject the binary representations. Like 1 means you will be represented as 0, 0, 0, 0. So 0, 0, 0, 1. 2 means 0, 0, 1, 0. 3 means 0, 0. Okay, 1, 1. 4 means 0, 1, 0, 0. This is 8, 4, 2, 1 format. Okay. So you make 8, 4, 2, 1. So whenever you want to represent 1, in 8th place you make it 0, in 4th place you make it 0, 2 place 0, 1 place 1. Okay. If you want to represent 2, then in 8th place you make it 0, 4th place 0, in 2 place 1, in 1 place 0. 3 means 8, 4 will become 0, 2, 1 will become 1, 1. Right? So, in this way, you will represent a decimal numbers. Decimal number system will be converted into the binary numbers. Like that, you have the base of 8, you have the base of 16. Okay. If you represent numbers in terms of the base 8, it is said to be the octal. And if you represent in terms of 16, there is a hexadecimal. In the hexadecimal, 0 to 9 will be represented as 0 to 9 itself, but the 10 will be represented as A, capital A, and 11 B, like that up to 15. So in the hexadecimal system, 16 will not come into the picture. In the binary number system, 2 will not come into the picture. While coming to the octal, 8 will not come into the picture. So it is always a modulo operation kind of thing, like 0 to 7 only you get. So this information is sufficient to move forward. So how to represent sets in computer? Assign a bit in bit string to each element in the universal set and set the bit to 1 if the element is present, otherwise use 0. Now all possible elements of the universal set are 1 to 5. Okay. If I want to assume a set A which is having 2, 5. So 2, 5 is there. I want to represent as 2, 5. So out of universal set, how can you represent? Because 2 and 5 are there. Remaining elements are not there. If not there, then they are 0. If they are present, then they are 1. So computer representation will be like this. A is equal to 1. In the universal set 1 is there, but in the assumed set A, 1 is not there. Hence, we'll represent as 0. Okay. And in the universal set 2 is there. In the assumed set also 2 is there. So then hence we'll make it as 1. In the same way, 3 is not there and 4 is also not there in the universal set and the assumed set. So 0, 0. But 5 is present in the universal set as well as in the assumed set. So hence we will make it as 1. In this way, the sets are represented in the are handled by the computer hardware. Okay. Assume B is equal to 1, 5. Now the first element is 1 and the last element 5 is also 1. Middle 2, 3, 4 will become 0. If you we'll consider the same example. A is equal to 0, 1, 0, 0, 1 and B is equal to 1 followed by 3 zeros 1. Now the union is modeled with the bitwise. So here any operation will be happened with the bitwise only. Please remember. Okay. Now A union B means in both the sets if the corresponding value is present, then only we will use the particular value. Now A union B, not in both the sets. Okay, you are supposed to combine both the sets. So 0, 1. Okay, so the A union B will become 1, 1, 0 will become 1. Here the first, second, third and fourth bits are 0, 0 and 0, 0 in both the A and B. Hence A union B also will get the 0, 0. While coming to the fifth bit is 1 in both A and B, so it will become 1. While coming to the A intersection B means it should present in the both the sets. Okay, the bits should be present in the both the sets. So First bit is 0 in A and first bit is 1 in B. So hence we cannot accommodate this in the intersection. So 0, so like that 1 0 it cannot be accommodated. So 0 0 0 and 1 is present in the A as well as B. So hence we make it as 1. While coming to the complement means 0 will become 1, 1 will become 0. So A's complement means wherever 0 is there, 1 you are supposed to place. Where 1 is there, 0 you are supposed to place. So 1 0 1 1 0. So this is the way of representing the computer bits. However, in deep, how only we will deal with the bits that you study in the computer organization hardware architectures. Let A and B are the two sets show that A intersection B and A intersection B complement are disjoint. Disjoint means nothing will be common. Okay. So disjoint of A intersection B and A intersection B complement is equal to null. Okay. That is the thing you are supposed to prove. Next, A is equal to A intersection B union A intersection B complement. Show that A, what is this symbol? The symmetric difference of A-B is equal to A. Suppose the universal set is U is equal to 1 to 10. Express each of these sets a bit string where the ith bit in the string is 1 and I is in the set and 0 otherwise. So this is the binary representation. Using the same we have seen in the previously 1 to 5 how we have represented in the binary representation. Like that you also represent assumption of the set 3, 4, 5 how you will represent 1, 3, 6, 10, 2, 3, 4, 7, 8, 9. Using the same universal set as in the last problem, find the set specified by each of these bit strings. So if it is 1 is there means, so 1 is present, okay, 2 is also present, 3 is present, 4 is present, 5 and 6 are not present and rest of things are present. So this is the way we can convert into the set representation.